Hi, welcome everyone. I hope you enjoy your lunch too. My name is Jacek. I work at SoftwareMill. We're a software consultancy based in Poland. There are two things that are unique about us, at least in Poland. We are a fully remote company and we have a flat structure. I think it may not be like that special here, but in Poland I think we are one of the pioneers. So today I'm going to speak about reactive, about stream processing. So let's start with a quick recap what stream processing is. And actually there's going to be a lot of code here, and we have a limited size of one of the screens. So if you have problems with reading the code, you may just try to look at the screen on your right hand side. Okay, so stream processing. Well, basically in a typical stream processing architecture, you need some kind of source of your data, and it's usually called the producer. You have a consumer which is the place where your data lands after it's processed, and you have a number of processing stages. So actually you have data flowing from left to right, from the producer to the processing stages up to the consumer, and the data, it flows in this direction. So what's actually special about reactive? Because, well, we're in a reactive track after all. So the special thing about reactive is how to handle a situation where you have a fast producer and a slow consumer. Because when it's the other way around, I mean the producer is kind of slow and the consumer is fast, there are really no problems, because, well, there will never be a situation where the consumer is flooded with data. But if the producer is fast and the consumer is slow, the consumer has to somehow deal with this situation. And how it deals with it really depends on the implementation. For example, if you look at the implementation of network stacks, like on the hardware level, it may be the case that, for example, the consumer is dropping the excessive data. But in the reactive approach, we use something that is called back pressure. And back pressure is basically data flowing. It's not exactly flowing in the opposite direction, but it's a way for the consumer to signal demand for data to the producer. So in the reactive specification, we have a mechanism which allows the consumer to ask give a certain amount of data, ask the producer for a certain amount of data, and this way it's never going to receive more than it's actually able to process at a given moment. So this is general terminology for stream processing, and since during this talk we are going to deal with Akka Streams, which is one of the implementation of the Reactive Streams manifesto, let's see what the names look like in Akka Streams world. So the producer is called a source, the consumer is called a sink, so this is the place where our data lands. The intermediate stages are called flows, and all those together form something that we call a graph. And actually the graph appears also in some other places of the API, but we will see it later when I show it in the code. So there is actually a lot of stream processing tools available. This slide comes from my colleague's talk about introduction to big data, and you have a number of stream processing technologies here. Akka Streams is even not among them. So let's see what are the characteristics of Akka Streams actually, how it is different. So first of all, Akka Streams is not distributed. So it's usually used on a single JVM, not in a cluster of nodes, for example. And actually this may not be entirely true, because when designing an Akka or programming an Akka Streams application, you have two parts, like in an Akka Streams application. The first part is the recipe for processing your data, and the second part is the runtime, and they are completely separated. So the runtime part is called a materializer, and this is the part that takes the recipe you have written for processing your data and turns it into actual something that can be run. And there is an API for the materializer. There is a default one provided by Akka Streams. It's based on actor systems. But actually you are free to implement your own materializer. And there was an attempt to implement one based on Apache Gearpump, which is one of the stream processing libraries, and it's actually a distributed one. So this is October 6th, but this was announced like a year ago, and actually I've recently talked to the Akka Streams guys, and they haven't heard anything more about the Apache Gearpump implementation. So the guys from Apache Gearpump tried to create their own implementation of a materializer, so a runtime for Akka Streams, but no one knows whether it actually succeeded or not. So in the default implementation, in the default actor materializer, it's not distributed because it runs on a single JVM. When writing Akka Streams application, you design like reusable building blocks. So the small parts of your stream processing pipeline are small recipes for processing your data, and they are of course reusable. So you can define how to process something and then reuse it somewhere else. And it's important that when writing those recipes, all of them are lazy until you actually run them. So you need to be explicit about saying that I'm done with my recipes, now I want to materialize them, so to create the runtime, and only then the graph is run. So all the definitions that we'll be writing here are going to be lazy until explicitly run. Okay, so let's see the use case that we are going to deal with today. Well, choosing a good example is always the tricky part. This one is actually taken from a real-life scenario that it's just a bit simplified, but we used it in an actual project. So our input data are going to be some comma-separated values. We're going to have simple lines consisting of an ID and a value. For every ID, we are going to have two lines. And it can be the case that either one or both of the lines for a given ID contain an invalid value, so one that cannot be parsed. Our files are going to be gzipped, and we're going to be extracting them on the fly, then grouping by the ID, computing the average value for every given ID, also gracefully handling the invalid values that may appear them, and eventually we'll be storing those data into Cassandra. Of course, it can be like anything at the end of the pipeline. It can be Cassandra, it can be any other database, but in this example that was taken from real life, we used Cassandra, so I'm also using it here. Okay, so let's go to the live coding part. And once again, if well, I'm using the presentation mode, but if the font is too small here, please, I know you either need to come closer or look at the screen at your right. Okay, so we're going to start with like a very basic building block, not yet related to Akka Streams at all. Since we're going to be parsing lines, we need to write some logic for parsing our lines. So let's write a method called parseLine, and actually the first argument will be for logging purposes. It's going to be the path to the file from which the line comes from, and the second one is going to be the line. And it's going to return a future, because well, also in the reactive approach, you need to try to be as non-blocking as possible. So of course, eventually you'll need to block somewhere, but all the intermediate implementations should be non-blocking. So we're going to use futures wherever possible. And we're going to return a future of something called reading. And reading is our domain model. So every reading has an ID, and we have a reading that is valid. So it also has a double value. But we also want to gracefully handle the case where the line has an unparsable value, and then we have another case class for it, the invalid reading. Okay, so we're creating a new future here. Now this is some like not too complicated code for just parsing the line with the semicolon separated values and returning a valid reading. But this is just the happy path. You may remember that we also need to gracefully deal with the invalid values. So let's just surround it with a try catch. We'll be catching anything here and doing two things. First, we're going to log it. That's why we want the file path to be able to detect in which file the invalid line was. And we're using the invalid reading, so the other part of our domain model, to return the information that we got a reading which has an ID, but it doesn't have a valid value. So this is the first part. As I said, it has nothing to do with Akka Streams yet, but we're going to start with Akka Streams right now. So the next thing we're going to implement is a way to actually deal with our stream of bytes, because of course we won't be reading the entire files into memory, we'll be streaming them instead. and we'll have a stream of bytes arriving, and then we want to split those stream of bytes into another stream of bytes, but the output stream of bytes consists of lines, so pieces of the file that consist an actual line. So we need to write some kind of a delimiter, so a component that is going to split the stream of bytes by a new line character to emit sequences of bytes that represent a line. So this is our line delimiter, and its type is going to be a flow. So a flow, as you remember from the introductory slide, is the processing intermediate processing stage in Akka Streams. It has three type parameters. First is the input type, so the type of data that gets into the flow. Second is the output type, so the things that get out and are passed to the next element in the pipeline. And there is also the third parameter, the mat, and this stands for materialized value. And actually, what is a materialized value? So the in and out types are, so to say, internal to the processing pipeline. So those are the types of data that flows within the pipeline. But those values, those types are not visible to the outside world. But sometimes you may want your flow or your component of the pipeline to emit something to the outside world, so it can be accessed. And this is the materialized value. So this is something you emit to the outside world. Most of the time we will not be using it, so we'll only be focusing on the types of values that are flowing inside the pipeline. But there will be one place where we are actually going to use the materialized value. So you will then see what is it for. So our input type is going to be a byte string. Our output type is also going to be a byte string. And byte string is basically an Akka Streams wrapper for a sequence of bytes. And for the materialized value, we have a special type that is called not used. You may wonder why aren't we using, I don't know, any, for example. The reason is that the Akka Streams developers really are doing their best to give a good API both for Scala and for Java, because many users of this library are writing Java. And in Java we have the void type for representing nothing. In Scala we have any, for example. And the reason for using not used here is that we want something like a common abstraction that can be used both in Java and in Scala. So no matter whether you're using Akka Streams in Java or Scala, you're just going to use the not used value. And actually it also carries some meaning. So it tells you what's that. Not only it's an empty value, but you explicitly say that you don't care about it and you don't use it. So for writing our line delimiter, we have a built-in component that's called framing, and we need to supply three things. First of all is the delimiter. So in our case it's going to be a new line character. Then we specify the maximum length of the line. Our lines are pretty short, so 128 is a reasonable default here. And there is a third flag called allow truncation, and we're going to set it to true, which basically means that we also accept lines that don't end with a new line character. If we set it to false and then our delimiter encountered a line that doesn't end with a new line character, it would fail. This may be, for example, a line at the very end of the file which doesn't have a trailing new line. So we want to gracefully handle it, and that's why we say it's allow truncation to true. So we have now written our first flow, so first processing stage of our stream processing pipeline, which basically takes the stream of bytes and turns it into another stream of bytes, but now consisting of actual lines from our files. So the next step is to actually parse an entire file. This is once again going to be a flow, since we'll be mostly dealing with flows here. Its input type is going to be a file, the plain Java IO file, so nothing special here. The output type is going to be a reading, so our domain model, and the materialized value we are once again going to ignore it, so it's going to be not used. Now when writing our own flow, we just start with a flow object which has an apply method that takes a type, the input type. So we're starting with a flow of file. And now for every file that comes to our pipeline, we are going to convert it into a source so in terms of Akka Streams, a source of byte strings. So basically a source of the bytes that are coming from the files. And now having multiple sources for multiple files, we want to somehow concat them and emit the values downstream, already converted to a reading. But the important thing here is that for every file we're going to have a separate source, and we want to combine the sources somehow. And in our case, we're going to concatenate them. For this, we're going to use the flatmap concat method, which basically for every file we can return a source, and the values emitted from the source would then be concatenated and emitted downstream. So what we got here is the instance of a file that we're going to process. And first of all, well, our files were gzipped, so we need to obtain a kind of an input stream for each of the files. So we take a new gzip input stream, use a file input stream inside, and it's going to be our input stream. And now we have a built-in helper for converting like the Java I/O streams into actual sources in terms of Akka streams. So we have the stream converters object. It has a method that takes an input stream, or actually a function that returns an input stream. And now we are going to like connect the source to the other building blocks we have. So first of all, we want to use our line delimiter to split the stream of bytes into a stream of lines. So we are going to use the via method to connect our source to another flow. So we just lose the line delimiter here. And now it may happen that our files contain header lines, for example, and we just want to drop them. So we have a configuration parameter for a number of lines that we want to skip from each file, and we're using the drop method to just like skip an initial number of elements. And now what we got here is a line represented by a byte string, and what we actually want to put to use when calling our parseLine method that we wrote at the very beginning, we want the line represented as a string. So we need to call map on the flow, and actually the byte string does have a UTF-8 string method that just converts it to a normal string that we can use. And now the final step here is to asynchronously execute our parseLine method with some given parallelism level to just parse the lines into our domain model. For doing asynchronous computations, we have a map-async method. It takes two parameters. First is the parallelism level, and we have a parameter here for non-I/O operations, so those that just happen in memory. And now we need to provide a function that takes a string and returns a future, because it's going to be an async computation. And actually, our parseLine method has this exact contract. We just need to like partially run it with the path of the file, which will be used for logging. And then the second parameter is that it takes is actually a string. So we'll just be passing our lines here and converting them into readings. So once again, about this flatmap concat stage we are using here. For each file, we are creating a source of byte strings, so a source of sequence of bytes. And then we are converting them into readings, into our domain model. And what flatmap concat does, it takes values from those sources, concatenates them, flattens, and emits them downstream. So that's why the output type of this stage is going to be a reading. So this is actually where the readings would be emitted from one by one. So now having this part, we can do the average computation. So basically group the readings by 2 and try to compute the average. So let's implement it now. And this stage is going to be once again a flow that takes a reading, like any reading. And the output type is going to be a valid reading, because for even if one or both lines have an invalid value, we would still like to emit some dummy value so that it can be stored to Cassandra, and we'll be using -1 for a dummy average when we are not just not able to compute it. The materialized value is still not used here. And once again, we're starting with the flow object and its applying method. we just say flow reading. Now we have the grouped method, and we're grouping our readings into groups of 2. And then once again, we're going to asynchronously compute the average for each pair of readings. But this time we're not going to use map async, but map async unordered. Now the difference between those two methods is that map async keeps the order of the arriving elements. So we have elements arriving in a given order. We have async computations executed for every element. And the order of the elements that are emitted downstream resembles the order in which the elements arrived. Map async unordered, on the other hand, emits the values downstream as soon as the computation finishes. So it may like break the order. In the previous case, we wanted to keep the order because we needed the readings with the same ID to be next to each other. But here we actually don't care about the order, so we can emit the averages downstream in any order. So that's why we're using the unordered variant here, which is of course quicker in most of cases, but it breaks the order. So you need to like be able to choose between those. We're once again using the parallelism level for non-IO operations. And what we get here is a sequence of readings, which is also always going to consist of 2 readings. We need to be async because this is the map async method, so we need to return a future here. And the first thing we do is to extract, well, now what I'll be writing right now is not perhaps the most efficient way to compute an average, but it's for the sake of simplicity, it would be like as short as possible. Of course, it's not about performance in this very piece of code. So please forgive me and like just accept the implementation as it's going to be. So we're going to take our readings, then just extract the valid readings from the collection. Yep, and it's going to be oh, I need a pattern matching here, sorry. So I need a case here as well. Yeah, much better now. So this is valid readings, and now we compute the average. So as I said, it's going to be pretty simple, but not necessarily performant. So we just check if the valid readings are not empty. If not, then we map those to their values. We take the sum and just divide it by the size. When we wanted to optimize it, we could, like, for example, handle the case where there is only a single valid reading, but as I said, it's not our main purpose here. And otherwise, so if none of the readings are valid, we're just using a dummy value of -1. And what we return is a valid reading, and now we need an ID, but since from our domain model, all the readings, be it valid or invalid, contain an ID, we are safe to just take the first value from our pair and use its ID, and use the average here. So once again, we define the flow that accepts reading as its input. It groups the readings in groups of 2, and then asynchronously executes some logic that is going to compute average, if possible, out of those 2. And this is it's doing it in an unordered fashion, which means it doesn't care about the order. It emits the results downstream as soon as they are ready. So it doesn't keep the order of the elements that arrived. Now the next step is going to combine the steps that we defined before into a single step for processing a single file. So it's going to be called process single file. It's going to be a flow that takes a file and emits a valid reading without a materialized value once again. And this is just to show how you can combine those different building blocks into bigger ones that can be reused later, for example. So once again, we start with a flow of file, and then we just use the via combinator to connect the subsequent stages. So the first one is the parse file, and the second one is the compute average one. Now it's important to note that the compiler guards us from connecting inputs and outputs with incompatible types. For example, if I switch the order of lines here, you can see that it doesn't compile because the types, like the in and out types of flows, don't match. So this is verified already at compile time, so you are safe about the types you are passing from one flow to the other. So this is the entire pipeline for processing the file. So we have the like a single flow, so the middle part of the pipeline. Now we would need a source, but we're going to implement the source later, and we need a sink, so the ultimate element of our pipeline. So let's define the sink now. So the store readings is going to be not a flow this time, but a sink. And sink has two type parameters. First is the input type, so what arrives, and we also have the materialized value. So the input type is going to valid reading here. And actually, this is the place where we are going to use the materialized value, because when we run the entire pipeline, we want to be able to wait until it finishes. So we will use a materialized value called future of done. So future is future, and done is another type which unifies the Scala and Java API. It's similar to not used, but once again, the developers focused on meaning being carried by the types. So we are not using not used here, but we're using done instead to signalize that we are actually interested in the fact that the processing is completed. And actually, when defining our sink, we'll start with a flow once again. This time it's a flow of valid reading. We once again use the map async unordered combinator. This time with different level of parallelism, because it's going to be an I/O operation, like storing to a database. So we have a configuration parameter for this one as well. And we have some kind of a reading repository that has a safe method that takes a valid reading and returns a future of something. This is actually a result set from the Cassandra driver, but we're just going to ignore it. So it's important that it's async, so it returns a future. And now what we want to do, we want to connect it to some predefined sink, which doesn't care about what gets inside, doesn't process the elements in any way, but just waits until the processing is complete and signals that. So we are going to use the toMat method, which is to. So to is used for connecting a flow to a sink, and the mat part stands for the fact that we are actually interested in the materialized value and we want to extract it. So we're going to use a predefined sink called ignore. And sink ignore is basically a sink that takes anything that comes, waits until all the elements arrive, and then completes the future that it's returning. So it's returning a future of done, because this is its materialized value. And with this future, it signals the completion of the pipeline. But this is not enough. So we need to supply one more parameter here. And let's get back to the slides for a second to see what we need here actually. So in the middle, you have the toMat combinator, and now to the left, you have the flow that we are using, which has its input and output types, and it has its type of the materialized value. And then on the right, you have the sink, which with like the input type matches, and it has its own materialized value. And now, while using the toMat combinator, you need to be explicit about choosing which materialized value do you want to pick, like whether you want M1 or M2. And actually, we're interested of the in the materialized value of the sink, which is to the right, as you can see. And that's why we are using the keep right parameter to indicate that we want the value from the right. In other cases, we could use keep left to take the left value. We could use keep both to take both values. And we could also use keep none for just ignoring the materialized value. So once again, we have two materialized values, so the M1 to the left, the M2 to the right, and we want to choose one of them. In our case, we're interested in the materialized value from the sink, which is M2. That's why we're going to use keep right here. Okay, so that's the ultimate part of our pipeline. So now having all those building blocks defined, we're ready to build and execute the entire pipeline. So we're now writing a plain method that returns a future of done, which is the materialized value of the sink we are using. it's going to signal the fact that the processing is complete. And well, we start with somehow obtaining the list of files to process. So it's going to be files. Now let's do some logging so that we see that anything is happening at all. Let's log this, record the start time also for logging. And now we have our flow defined, we have our sink, but we need a source. So that's the moment when we'll be defining the source of our data. So the source in its simplest variant just takes an iterable, so we can pass files here. Now we use the via combinator to connect it to the process single file flow. And then we are using the run with method, which does two things. Well, first of all, you can provide a sink that you are going to use for running and actually run it. We could also use the two method to attach the sink and then run, but since this is a very common scenario, there is a single method for that called run with, and it just takes a sink. Now this returns a future, so we can use the and then combinator on the return future to just do some logging afterwards. This is not necessary, so like the main part which is enough to run it are those 3 lines, but we also want to do some logging, so let's just add a bit of logging here. Okay, so well, looks like we are almost there. So let's see what the compiler has to say. So let's run SBT here. And try to compile that. And actually we have some problems here. 2 of them are about a missing execution context for the futures, so the thread pool that is going to be used for executing the futures. And the third one is about the materializer. So as you remember from the beginning, we have now only defined the recipe for processing our data, but we need an actual runtime that is going to be used to run our computations. So as I said previously, the default and the only one so far, materializer, is the one based on an actor system in Akka. So let's assume we're going to have an implicit actor system available here. And actually you can see here that the run with method expects an additional parameter, an implicit one, and this is the materializer. So that's why the compiler is complaining that we didn't provide a runtime for our graph. And we also need a thread pool, the execution context. And now I'm going to do something very dirty that you shouldn't normally do, but for the demo purposes, I hope you find it acceptable. So I'll say import system.dispatcher, which is an execution context, but it's the thread pool that belongs to the actor system. So normally we shouldn't be using this thread pool for executing our I/O operations, because there is a danger of starving the actor system and starving the communication between actors. So normally what you should do is have a separate execution context for the I/O operations and use this one. But since here I just wanted to compile for the demo purposes, so the execution context that comes from the actor system will be enough to satisfy the compiler. But don't do it in production. So now we have the execution context, but we are still missing the materializer, so the runtime. So let's just create one. So we'll just say implicit val materializer. And we have an actor materializer apply method, which actually takes the actor system as an implicit parameter. So now we're all good. So we have defined a runtime for our pipeline, and the compiler is happy. So actually there is one more thing to this code, because what we are doing now is that we are processing the files like one by one. And what we actually would like to do is have the files processed like in parallel. So basically we would need something like a load balancer that would take the files that are coming. We would have a worker. In our case, a worker is the process single file flow. And we want to execute like a number of instances of the process single file flow to just process the files in parallel. and then like combine all the results together and emit them downstream as valid readings. So let's try to implement a simple load balancer and a bit generic one that we could use here. So we have an object balancer, and we have a method called create that takes two type parameters for the input and output. And it has two parameters. First is the number of workers, so the number of parallel instances that we want to have. It's, well, an int. And we also need the worker, so the actual flow. And it's going to be a flow with the generic types in and out, and actually any materialized value. In our implementation, we're going to ignore the materialized value and just like combine the values together to emit them downstream. Now to implement it, we're going to use something called GraphDSL, which is a bit low-level tool to implement your own processing stages, so flows, for example. It provides us with a create method, and this method gives us access to an instance of something called a builder, which is basically a thing that we can use to manage the structure of the graph. And now we are going to do two things. First of all, we'll be using two built-in stages here, one for balancing the work and the other one called merge to combine all the results together and emit them downstream. So we're using builder add to add a built-in stage to our graph. So the first one is going to be the balance stage, which, well, it takes a type and it takes the number of outputs that it's going to have. Balance is one of the so-called fan-out stages, which means that it has a single input and a number of outputs that we define. So it just fans out the values that come in. In our case, it's going to be the number of workers. We'll call the stage balance. Then we need another built-in stage called merge, which also has a generic type. This time is going to be out, and now merge is a fan-in stage, which means it has a number of inputs and a single output. So it's like a bit similar. I mean, we can connect those two together. So this is our merge stage, and what we are going to return is a flow shape, actually. So it's a flow shape means that it's a flow, so it has a single input and a single output. So we need to provide those. So as the input of our stage, we're going to use the input of the balance stage, and as the output, we're going to use the output of the merge stage. And actually now, if you look at the return type, you can see that it's not a flow, but it's a graph that has a shape of a flow. So this is what I mentioned at the very beginning, that the graphs appear also in the API somewhere. So basically every part of the processing pipeline is a graph with a given shape. And in our case, the shape is a flow shape, which means it has a single input and a single output. And the graph has a materialized value as well. And this is actually not enough. So what we want to do to make it work is to connect each of the outputs of the balance stage to a new instance of our worker, and then connect the output of the worker to one of the inputs of the merge stage. So we need to like iterate from one to number of workers, and for each worker that we want to use. Oh, and I need to import some fancy DSL here. It's GraphDSL implicits. And now I'm able to say that we want to take the balance stage, use its output, connect it to the worker, and connect the output of the worker to the merge stage. And this is actually creating a new instance of the worker and connecting the inputs and outputs accordingly. Okay, so now we should be able to run it. Well, we just need to use it here. So now instead of piping our source via process single file, we'll say balancer create here. We have a configuration parameter for concurrent files, and we'll use the predefined like the one written stage that we wrote before, the process single file here as the worker. Okay, so we have Cassandra running in a Docker container somewhere here. We have an Akka Streams readings table that is now empty. So oh, actually, sorry, we're missing a method here, like the run actually is going to be fast. So we just create the configuration, create the actor system, and run our method. Okay, that's this one. So now we see that there are some invalid lines actually because they are logged, and we see from which file does the invalid value come. And now we see that the processing is done, so let's inspect our table. And we can actually see that there are indeed some values here. Okay, so that's the code I wanted to show. So of course there is a lot more about Akka Streams. You have already seen the graph DSL. Of course, you can use it to create less trivial stuff as well, using some more advanced features of it. You can build your own flow, so you can use an even lower level API than the graph DSL to implement your own flow. Then you can deal with state, with the internal state of a flow. I've actually written a blog post about it. There will be links at the very end, so I encourage you to have a look. And you can also use a library or a set of libraries called Alpaca, which comes from Lightbend as well. And this is basically a kind of reactive integration. So Alpaca is a set of connectors for reactive streams to different files, databases, like for input and output. So anything you can imagine. It's under heavy development. If you'd like to engage into open source, I think this is a good time for writing your own Alpaca connector, for example, because there is not too many of them at the moment. There is also Monix. Monix is another implementation of the reactive manifesto, so the reactive streams. I've also written a blog series about the comparison between Akka Streams and Monix. The links will be at the very end as well, so if you want to take a look, please do. And one more small commercial, we at SoftwareMill are issuing Scala Times, which is a Scala newsletter. So if you want to stay, if you haven't already subscribed, I encourage you to subscribe to get like once weekly newsletter with a lot of interesting stuff. So that's all I had. Under the QR code, you have the link that is here as well. This is a landing page with the source code, with all the links that I mentioned previously. If you have any questions, you can come now, you can ask now, you can stay here. We have like 20 minutes after this talk, I think. So thank you for your attention.
Thanks. For a live coding session, that wrapped up perfectly. It worked in the end. Like Jacek was just saying, our next session here doesn't start for 20 minutes. So if you'd like to stay and ask questions, we have plenty of time. Any questions?
Yeah, a question on the, could you go back to the code?
Yep.
You group pairs of lines that have the same ID, group by two. Is it possible to group by ID? How would you change the code to look at two lines and pick the ones that have the same ID rather than just, because if you get off by one, you're going to...
Well, actually, there is the question was how could you basically group not by a number of values, but by a field and by a similar value in this field, right? So, for example, to say that you want to group until the ID changes, right? Yeah. So, well, there is no built-in stage for this, but actually, I've written one myself, and I contributed it to. It's called. There's a repository called Akka Streams contrib, and actually I needed this, so I've written this one. And the blog post that I mentioned about writing your own stage is actually about writing. It's called accumulate while unchanged. So basically, you provide a field for. I think I don't have Akka contrib in dependencies here, but you just say accumulate while unchanged. You provide the field, so ID in this case, and then it basically accumulates the elements, so maintains its internal state, accumulates them until the value changes, then emits the accumulated ones and starts accumulating once again, waiting for the next value. So this is, well, as you see, like not everything is built in, but it's not that difficult to write your own implementation. So you can have this blog post as an example for this one.
Thank you.
Thank you.
Any other questions before we thank you?
I'm here until the end of the conference, so yep.
One in the back. We've got time.
So I've written a small Akka Streams application, and you talked at the beginning about back pressure, and initially that's one that people talk about as being a feature of Reactive Streams, and this is an example. But curious as to why, conceptually, in my mind, the ability to fan out, which you don't get in a full system like Spark, right? In Spark, there's no you can't fan out. There's just all the pain. When somebody tries to tell you like now you got to make these undetermined number of things, there's just this pain. So like I'm curious as to why, back pressure is the one you mentioned, and being pull push so to be able to have fan out doesn't come as significantly in your mind.
Actually, I'm not sure I'm getting the point of your question. So
That's okay. I'll talk to you later.
yeah, okay. So sorry about that.
No worries. Great. So let's just say thank you to Jacek one more time, and we'll see you at 10 after 2.
Thank you.